All right. Now I've been looking forward to this. So, Dirk, thank you so much for joining us.
Thank you for having me.
I started my career as a hardware guy. And my very first project, I was sharing it with somebody earlier. I was an engineering intern at General Motors, and I got to work at a 17-year-old. I got selected to do it. And I was building the third tail light. That was my project. And now to hear the very concept of a software-defined vehicle, just in my lifespan to go from that when we were working in the physical, it was barely any software in a car at that time, if any, to where we are today. So we're gonna do a little deep dive, and there's three big areas we're gonna talk about on the software-defined vehicle. And Dirk, you want to share a little bit about who you are and where you work and what you do?
Yeah, sure. So Dirk Schulte, I am the R&D Director for Advanced Engineering and Product Platforms at Valeo, the brain division here in North America. So Valeo is, I don't know how much familiar you are with the automotive world, but Valeo is one of the global automotive tech companies. We call ourselves a tech company. That sounds nicer than being a component supplier. And but the truth is that over the recent years, as you mentioned, the automobile industry has shifted away from the old hardware industry or mechanical industry more and more to tech. And that is exactly where Valeo is anchored in. So Valeo has three main divisions. Valeo Light, we are working on everything that is around exterior and interior lighting, power, everything that is powertrain, batteries, battery cooling, and so on. And then Brain, which sounds a little bit like a funny name, but is actually everything that is centered around autonomous driving, driving automation, interior experience. So everything that is sensors, components, hardware, and software, more and more software specifically.
Awesome. So we kind of already jumped into it, and we were using the phrase software-defined vehicle, but that term is reshaping the industry. For those who may not be totally familiar with it, how do you define a software-defined vehicle, and why is the industry transforming to it now?
Mm-hmm. So yeah, the software-defined vehicle, it has become almost a little bit like a buzzword. Everybody's talking about that. So what it means is really that we are moving away our focus point or a corner point of the development away from the old mechanical worldview or hardware-driven worldview, and now it's the software that takes the center stage in the development, right? And that is enabled actually through more compute power. We have seen that first coming with the robotaxis, well known specifically here in the San Francisco and the Bay Area, with Waymos and other robotaxis driving around here. So they built the foundation for that to some extent, and now compute has become more and more affordable and accessible. So that opens the door to shift away from the older, let's say, hardware and then mechanical centered design of vehicles to putting the software in the center of everything. Meaning that we have more and more, we are seeing more and more instead of these fractured, segmented architectures where we have multiple compute units, ECUs inside the vehicle that all doing little tiny sub functions, we all centralize into one big compute unit, sometimes with a zonal unit to speed up, let's say, the processing between the different sensors on the different zones of the vehicle, going back to the central compute. And then, of course, the software AI-driven and fusing different sensor modalities together then.
Now, this next question wasn't scripted, so don't get mad at me. Where's Wade? Is he still here? Blame this on Wade because he made me think of it. At the heart of the SDV, then, we have to be almost continuously connected now to the network, right?
Absolutely.
So if I think about in the European theater and that issue that Wade was bringing up about we're going through different countries, how are we handling that within these now connected cars like this?
Mm-hmm. So, I mean, yeah, connectivity is indeed one of the big cornerstones of the software-defined vehicles, and especially also because with focusing more on software, we need to make sure that we decouple the software lifecycle from the hardware lifecycle, right? So software connectivity is a need, is a must. And we need to make sure that because it would be useless if we have a nice centralized computer and software, but we cannot update it, right? I mean, we have, especially when you think of machine learning lives from data. The more data we have, the more we can train, the better our algorithms become. So we need to have the possibility to train continuously our models. So connectivity is certainly one of the cornerstones. That is one of the enablers also of the software-defined vehicle, because connectivity became much more capable and accessible also, specifically also in automotives. We are moving from 4G to 5G, looking into 6G now. Yeah. Then thinking of the different regions inside the world, it all works somehow with partnerships, right? The automotive companies don't necessarily have the capability or the competence to define networks, to define connectivity and so on. And we are partnering then with other companies. And that's, I would say, one of the reasons why I'm here, because Valeo has decided to partner with Verizon actually. And we are doing the network or the connectivity part together, specifically for functions like V2X, where V2X meaning vehicle to everything. So where the vehicle communicates constantly with its surroundings for things like updates, but also for things like real-time access or assessment of what is around the vehicle for safety, critical features, and so on. And that is done by local network providers and then specialists in these fields.
Oh, that's great. And so now you know not everything is scripted. So Wade, thank you wherever you are. I noticed it really when I was leaving my hotel this morning, and there are Waymos everywhere. I was actually shocked how many are around. I spent a lot of time in Atlanta. We have them there, but it was one after another. We think about this trend with the robotaxis. It's now becoming, we're moving up the level stack, the SOE autonomy stack for the cars. We're moving up. What did the robotaxi era, what is it teaching us as an industry? And how is that knowledge working its way into the everyday passenger car?
Yep. So I think robotaxis to some extent made it happen. There were the first applications where really massive central compute was tested and deployed. And from there, it somehow trickles down now to the passenger cars with a very important scale effect. I mean, robotaxis, you said there are a lot of them for sure. Here in the Bay Area, you have a lot of them. If you go in other regions in the US or elsewhere on the planet, not everywhere you have such a dense net of robotaxis as you have here. And so it is nothing compared to standard passenger cars, right? So there's a scaling effect that needs to take place. So we need to scale the capabilities of a robotaxi, which is extremely complex. When you look at the sensor suite that a Waymo, for example, has, it is much more capable than what you have nowadays, at least on normal passenger cars. So the quantity of sensors and what you find in these vehicles, the perception algorithms that they are using, the fusion between the different perception modalities, the compute, all of this is, let's say, a level above what you would find today in passenger cars, but it's trickling down. So robotaxis made it possible. They laid the foundation to have all these sensors, all this compute, all the software, the AI applied to it. And they now make it possible to level it down, let's say, phase by phase to normal passenger cars. And that also is reflected then in this categories that SAE formulated with level 1, 2, 3, 4, 5, and so on. Robotaxis typically are classified as level 4, so as autonomous vehicles. And you can scale it down basically to what becomes a convenient, then not an automated driving, but a driver assistance function, an ADAS function for passenger vehicles, and make driving safer and more convenient for the everyday driver.
Okay, great. Now we're going with, no pun intended, I'd say, now we're going to go under the hood. But that was pretty clever on my part. So walk us through the architectural change under the hood, from the dozens of distributed ECUs to the centralized or zonal compute. What does that unlock? and what really makes it hard to do this?
So yeah, I mean, as you mentioned before, I mean, first of all, it's not dozens. I mean, it depends on how much you multiply dozens with what. But I mean, it's more than 70 to 100 compute units ECUs that were in the cars or are still in the cars nowadays in this completely fragmented architectures that we have. And these are all separate ECUs that all run their own firmware that are not connected. So once they're in the car, they are there, they're doing what they're supposed to do, hopefully, but you cannot do anything else with them. You cannot teach them anything new. You cannot get them to perform new functions. So it's a static system, right? With the software-defined vehicle and the central compute, we are unifying all these different functions that are residing today on separate ECUs into one big central compute unit, right? So what does it unlock? Well, we get everything to sit on one central compute, which is connected, as you mentioned before, right? So we can update it, we can learn it new tricks if you want. We can make it safer over time by improving the algorithms that are running on it for safety, for example. We can also implement completely new features that were not there when you bought your vehicle. One nice example, and this is perhaps the commercial block here that I'm doing for Valeo. So we have a nice product that went just into production recently, and I'm a very big fan of this. It's called Valeo Racer, and it's actually using the perception sensors that we have on the vehicle and the cameras on the vehicle and transform it through an AR, augmented reality interface into a video game for the passengers of the vehicle. So you are playing literally Mario Kart inside your vehicle, looking on the road in front of you.
My son does not need this.
Yeah. So this is something, I mean, that was not on the vehicle before because there is no, I mean, nobody really asked for that, but it's actually a very neat feature. It's also, it has some nice perks, like for example, it avoids motion sickness because you're looking at what the vehicle is actually doing. So what you are feeling is not decoupled anymore from what you are doing in the video game. It reduces the stress of the parent driver, let's say, to not have the kids in the back of the vehicle shouting all the time, "Are we there yet? And how long is it still going to go?" And it is a completely new feature for all these perception sensors and compute units that we have in the software, and that has been added on later on the vehicle. So just as an example, that we can add new features to the software-defined vehicle at any moment. And perhaps as an additional point also, specifically as we are heading towards electrical vehicles, for the duration of the battery in the vehicle, obviously we have to take care of the weight of the vehicle, right? If you imagine you have 70 to 100 little ECUs everywhere in the vehicle that needs to be connected in some way, you have cables running everywhere. There are miles of cables inside a vehicle nowadays. So if you have a central compute specifically with the zonal architecture, where you connect the sensors at the different locations, for example, front left, front right, you have cameras, ultrasound sensors, radar, and so on, with the zonal controller, and from there it is passing through to the central compute. You reduce drastically the amount of cables, which is A, a cost saving, and B, it is a huge weight saving also. So that also contributes then to the overall economy of the vehicle. So all these are enablers. Now you were asking about the problems with it. Yeah, I mean, if you have a lot of things running on one single central compute, you have the obvious problems like priorities, what comes first. And I mean, in a vehicle, obviously, the first thing that always comes is safety. Right? And then you have other things on these central compute units you have running together, infotainment. You have in some cases even things like engine management for electrical vehicles, battery management, all running on the central compute. But safety always comes first. And then the other functions. So we need to find a way to manage the different, let's say, importance levels of what is running on the central compute units.
So when can we expect Mario to be out in commercial?
It is out.
It's out.
It is out.
All right.
It's not.
All right.
Don't call it Mario. It's
Oh,
we don't have a license from Nintendo for that.
Fair enough.
No, but it is out actually. Not here yet. But the first application is actually in South Korea.
Okay.
Interestingly, with Renault. And so yeah, there, if you travel to Korea in the next time, you should rent perhaps a Renault vehicle and try it out.
All right. So Dirk, Valeo sits right at the center of all of this as a tier one supplier. How is the role of Valeo changing in the SDV world? And do you think you guys are becoming a software company?
That is a very good point. Yeah, I mean, actually, that is exactly the point. Yes, we are becoming a software company to some extent. Yeah, we have to move away from the traditional worldview of being extremely hardware and component centric. We always had software capabilities, but we have ramped up dramatically our software capabilities. We have big software development centers all over the world. In Egypt, more than 3,000 people, if I'm not mistaken, in Egypt. We are ramping up our software development capabilities in India, in China. We also created, I think 2 years ago, a tech center in North America, in Mexico, with a strong focus also on software developments. Yeah, we have to move. We have to get much stronger on the software side for sure. And so that is one thing. And I mentioned before already the partnerships, and not only with companies providing specific technologies, but also with the OEMs. When you look at the OEMs, what's going on there, what you see in the news, the people that are joining OEMs, very often they come from software companies, from computer companies, and there's a reason for that. And there is also a part, whatever we do as a tier one supplier, however good our components and our software can be, there's always a part that is, let's say, the personality or the design language of the vehicle itself, and that identifies the OEM, like the headlamps identify it, and like the interior design identifies. So that is something that the OEMs is not going to give away, right? So we have to partner with them. We are partnering with the OEMs and interfacing directly with their teams to create compound teams, if you want, to develop specific features where our knowledge goes into the development as well as the OEM's knowledge.
Oh, awesome. So then we kind of set the foundation here. We're going to go a little deeper, talking about the levels of autonomy. So not everybody here may be familiar with these levels, but when they hear levels 2, 3, 5 everywhere now, give us the plain English version of what the SAE level 0 to 5, what does that really mean to each of us?
Yeah. So that is, it's a very nice topic, actually. I mean, level 0, obviously, as the name almost indicates, means nothing. I mean, there's no driver assistance at all, nothing going on there. Level 1 would be, you could call it one-dimensional driver assistance. So there's one modality that is assisted by software, by compute. For example, lateral control for lane keeping, longitudinal control for braking, distance control, and so on, but not a combination of those. So typically, to give you an example, AB, which now every vehicle has here in the United States, AB is typically a level 1 feature.
Okay.
Simple lane keeping without interfacing with any other feature in the vehicle is also a level 1 feature. Now, level 2 is a combination of these. So here we are talking about a two-dimensional approach. So we are combining, for example, the longitudinal approach. So adaptive cruise control, for example, traffic pilot. And we are combining that with lane keeping, so that the vehicle on a highway, for example, can steer, always keep the right distance to the vehicles in front of it, and stay at the same time in the middle of the lane. That would be a level 2. Then there's the famous level 2 plus. We can talk about that a little bit later. Level 2 plus. There are more pluses now being thrown in the mix. Then we go to level 3. So there is a very important step from level 2 to level 3 on different levels, no pun intended. First of all, up to level 2, the responsibility for the driving is with the driver. So the driver drives, commands the vehicle, and is fully responsible for whatever the vehicle is doing. Level 3 is the first level where the machine becomes responsible for driving, right? Now, this continues up to level 5. So level 4 then is also a machine-driven or computer-driven vehicle, automated vehicle. The difference between level 3 and level 4 now is that in level 4, you have a fully autonomous vehicle in a defined ODD, in a defined operational design domain. So that means that there are some restrictions, for example, specific roads. It can only drive on specific roads in a specific geofenced area. It can only drive under specific climate conditions, not in snow and so on. But it does all of that autonomously, whereas in level 3, the, let's say, fallback solution, if something unexpected happens, is the human driver. So in a level 3 vehicle, you have still the human driver, even though the human driver can be inattentive, they have to be able within a reasonable amount of time to take back control of the vehicle. So in other words, the fallback solution is the human driver. In level 2, going backwards a little bit, the driver has to be attentive all the time. No way, at no minute, the driver cannot know what's going on around them, can move to the back seat and try to find a book or whatever that they lost. So they have to be attentive all the time. Level 3, the machine is driving. But typically you have around 8 seconds take over time that the driver should be able to take over the steering of the vehicle then again. So then we talked about level 4, and I mentioned before already level 4, this is typically where the robotaxis sit. And level 5, well, that today doesn't exist yet, because the difference between level 4 and level 5 would simply be the disappearance of the ODD. There is no operational design domain anymore. The level 5 vehicle would be able to drive autonomously everywhere under every condition. That today doesn't exist yet, right? Robotaxis level 4 is the state of the art, let's say, in driving automation today.
A side question from that. We as humans, we don't always adapt well to change. But as we cross that big threshold from 2 to 3, do you believe that the insurers and the industry and the governing bodies and the governments, are they fully prepared when this transition happens?
Well, I cannot really talk for the for insurance industry or for government regulation initiatives and so on. What I can say is that actually, when I mentioned that there is a big gap or big parting line between the level 2 and the level 3, it's exactly that. It's the legal foundation as well, because up to level 2, the driver is in control of the vehicle and is responsible. If something happens, if an accident happens, the human driver is responsible. If they didn't pay attention, then obviously it's their responsibility. If they did something wrong, it's their responsibility. From level 3 on, it is the system that is responsible for the driving because the system is officially driving. So, but the question is now, who is the system?
Right.
Is it the OEM? Is it the person who developed the software? Who is it? And that's still, there are still discussions, I think, going on. But typically, from level 3 on, the car manufacturers have to assume responsibility for what the vehicle is doing. And that is obviously a very, very big step, perhaps even more than the technological step. It's the legal step here, because imagine your car goes out on icy roads or something, has an accident. So whose responsibility is it?
Right. So I'm going to backtrack a little bit. When a few weeks ago, I was in Munich and I was with some of your colleagues, and one of them, somebody said 2+, and I'm like, I didn't know what that was, because is that a real category? Is that a marketing thing? So what can you a little more light on this 2+ thing?
Yeah, so the L2+ together with the L2++ and the L2+++ and how many pluses you want to add is pure marketing, actually. So, but there is a reason for it. Or when I say pure marketing, it sounds a little bit harsh, but it is correct when I say that, because when you look in the SAE guidelines, there is no L2+, right? It's L2, L3. People have come up with L2+ and L2++ and so on, because of what I just explained, because the gap between L2 and L3 seems to be so big that there are a lot of functions that reside in this gray area between that are very valuable to the end user, but they are not properly marketed because you are downplaying them somehow if you are selling them as level 2. Because as I said, theoretically a vehicle that keeps its lane and that keeps the distance to the vehicle in front of it is an L2 vehicle. If you think of Tesla, vehicle with supervised FSD, or a GM vehicle with Super Cruise, for example. They change the lane automatically. They change the lane, they change back. They do the takeover maneuvers automatically. Sometimes, in some cases, they can go from point to point. So that is also level 2 because the driver is still responsible for it. But I mean, to distinguish that a little bit from the very simple L2, people came up with the L2 plus and the how many pluses you want to add to that. But it is not an official SAE category. It is more really to show that this L2 does more than the simple L2 version.
Yeah, that kind of reminds me of several years ago when there was a carrier that was going around saying over 5G. I don't think it was our colleagues in here, but I do remember that when it wasn't really 5G. But okay, thanks. That was very insightful. So as you describe, this level of autonomy thinking is inevitably being now applied to humanoid robotics, and we're starting to see, this crossover here. How does that mapping work? And what does automotive autonomy have to teach the robotics teams and vice versa?
So yeah, the embodied AI or humanoid boom, if you want to call it like this, is actually it's a very interesting phenomenon, a very interesting thing that is happening, and it's following in a lot of senses the automotive industry. I mean, when you think of a robotaxi, is somehow nothing else than a robot, an embodied AI, if you want, to some extent, only on wheels. So that's why, at least at the moment, some of these categories in terms of autonomy have been adopted also for humanoids, with the most, interestingly, the most frequent realizations in the humanoid world being somewhere between level 2 and level 3. So you have also either teleoperated humanoids, which you can see a lot. I mean, on a lot of fairs, when you see the humanoids dancing and then jumping around, in a lot of cases you have people with a joystick behind it. So that is then teleoperated somehow. You have also then more autonomous realizations, but they are still within a pretty well-defined ODD. So for example, if you think of a humanoid in a factory space, they know how to grab a certain box, to take it from one side, to put the pallet at the other side in a different shelf. But that is a very limited and trained operational design domain. So that is also where, again, this category 2, 3, and so on comes in. Okay. And I think, I mean, the big difference is today that the humanoids have a significantly higher level of degrees of freedom than a vehicle has. A vehicle is basically two-dimensional. It can either go left or right or backwards and forwards. So a humanoid can do exactly the same, regardless if it's a bipedal or if it's a wheeled robot. But then you have all the grasping, right, and all these other functionalities, and that introduces a complete new range of functionality and of degrees of freedom that today don't exist in vehicles, right? And so how to treat this can certainly also infuse some additional knowledge then back to the automotive world.
Okay, perfect. So we're going to go to another topic. We're talking about a fusion of sensors and safety here. A little while ago, in the earlier questions, you said that AI, and there's a basis of whenever we have AI in there, the safety has to be the priority on there. Can you talk a little bit about this sensor fusion and why no single sensor is enough?
Mm-hmm. Okay, so no single sensor is enough. You will certainly find people who are debating this. There are several car companies who think that they can provide a full safety cocoon and even self-driving capabilities with vision-only systems or camera-based only system, which makes sense because humans are driving vehicles for more than 100 years, and we only have our eyes, right? So, and we are able to drive more or less successfully most of the time, but we are able to. So why shouldn't a vehicle with a camera be able to do the same? And it is true, you can do that. Actually, a single sensor modality could do that, yes. It is, however, it makes sense to use more sensors because if you have them available, why not use them,
Mm-hmm.
right? And they always bring additional benefit. And going back to the robotaxis, today, most of the robotaxis out there, they are using actually multiple sensor types and fusing them. And why? Because no single sensor can cover the whole range and can really do everything. For example, if you take AB, right, automatic emergency braking, today in, well, I would say most of the applications out on the market, they are camera only based, right? However, if you fuse the camera information with a radar information, you get much better results. Why? Because the camera is very good in classification. So it can tell you this is a human, this is a bike, this is a car. It can read a traffic sign. The radar cannot really do this, but the radar can tell you how far is the object away very precisely, centimeter level precisely, and it can measure its speed and compare it to the ego vehicle speed. So it can tell you if you're approaching a vehicle, is there a risk of collision or not? The camera can do that as well, but it's approximation. It's not measurement, it's extrapolation, it's approximation, right? Combining these two makes the system much more robust. And that's why we believe that, sensor fusion is really something that, even though it might not be absolutely necessary, because again, people are doing without it, but it certainly makes things safer and provides additional information that contributes to the safety goal.
Okay, all right. AI perception is probabilistic, but in safety, we do need guarantees. How does the industry validate AI-based safety systems, and what makes that so hard?
Yeah, in the automotive industry, we have two main safety guidelines, if you want. We have the ISO 26262, which looks at how the system behaves when a component fails. And then we have also, it's a little bit newer, we have SOTIF, which looks at if the system behaves safely within the intended functionality. So this is what we are following in all our designs, in all our layouts, in all our developments, and also the validation. And then so this is, let's say, the baseline or the cornerstone of our developments. Then if we go and if you look into validation, so you mentioned AI, and specifically in the automotive industry, you have a lot of machine learning algorithms where we teach specific situations and try to get this data set bigger and bigger. So it is extremely difficult to gather enough data to cover all the corner cases. I mean, it's impossible. Every day there are new corner cases coming up, right? And that is also why in the automotive industry, a lot of people say data is gold. I mean, that's the new currency. Right. The more data you have, the better you can train your models, the better potentially your algorithm can become. So to add to the real world data gathering, we see more and more simulation. So we have very capable simulation foundations that can simulate real traffic situations in the real world, and can even out of this extrapolate and create new situations, create new edge cases. And then there's also, I mean, the classical way, the old way, let's say, is to have specific cases, and that's more, let's say, in the regulation space. For example, where you have FMVSS regulations and so on, where you have to test your vehicle against specific defined safety situations, which we have to accomplish as well. Right, but I think the combination between real world data gathering and simulation is really what drives the AI generation of software at this moment.
Okay. As we see the levels of autonomy increasing in the cars, how do we keep drivers appropriately trusting of these systems, neither over trusting or under trusting? Where's that balance?
Yeah, that's a very good question. Actually, interestingly, the biggest source of, on the one hand, drivers' frustration, and on the other hand, of accidents, is actually over-reliance on what the vehicle is capable of doing. So that has to do partly with, I'm looking for the right word, information, perhaps. So people misinterpret or misunderstand what the capabilities of the vehicle are, sometimes through exaggerated promises or reports or whatever, and they think their vehicle can do much more than it actually can. So it is really necessary to make sure that the user, that the end user, the driver, understands what the limits of the automation, of the assistance that the vehicle provides are, to not be over-reliant and climb in the back of the car thinking they can sleep there while the vehicle is a simple L2 vehicle, right? That is one thing. And well, then directly linked to this is also HMI, so the human machine interface. We need to inform constantly the driver, specifically, again, talking about L2 vehicles. We need to inform the driver what the vehicle is doing, if there is a dangerous situation coming up, if there is a takeover required, and so on. This needs to be communicated to the driver very quickly and efficiently. And we need to keep the driver in the loop. Again, we're talking about L2 here specifically. So I think everybody has heard about driver monitoring systems. So we have now sensors not only outside of the vehicle, but also inside the vehicle. A camera, infrared camera based normally, that is monitoring the driver constantly and checks the attentiveness and, in the worst case, drowsiness or inattentiveness, incapability to drive of the driver, and then takes the appropriate action by either warning the driver or even going to a safe state and pulling the vehicle over, or this kind of safety maneuver. So we have to make sure that the vehicle also knows what the state of the driver is and is able to react on this.
So you mentioned HMI. Let's go farther inside the vehicle now. How is AI transforming the in-cabin experience beyond the obvious voice assistants?
Mm-hmm. Yeah. So we have in the cabin, we also have sensor fusion, because I mentioned that there are also sensors inside the vehicle. And the sensors that I mentioned at the outside of the vehicle, cameras, radar sensors, and so on, we have actually the same inside the vehicle. And we can combine them as well. We can combine them to make the vehicle safer. We have combination between cameras, between radar sensors, for example, for use cases like child presence detection, so that children don't get left behind or forgotten in the vehicle. The driver monitoring we mentioned already. Radar gives us a good idea of position of the person in the vehicle. So, for example, for airbag deployment, we know exactly where the person is sitting. We can check vital signs of the person, heart rate, breath rate, and so on. So all of this is fused together, and then the AI evaluates these information and can give a better driving experience. And then you have obviously all the infotainment part where generative AI takes over now. So you mentioned the voice command. So it's not just a parsing system. It's becoming somehow almost like a co-pilot. And we have seen cases where the AI in the vehicle, the generative AI, talks in some cases not only, or can talk in some cases not only to the driver, but also to the passenger to tell them, oh, I think your driver is not paying attention, nudge him perhaps and make him look on the road. So that's examples where the AI can really involve the whole information from the different sensors and all the occupants of the vehicle to make it a safer and more intuitive and enjoyable driving experience.
So we talk about all that sensors on the inside, observing not only the driver, but the passengers. Does this raise real data and privacy concerns? And what's the industry think about that balance?
It absolutely does. And I mean, that is a very, very actual, very important question. And you have seen certainly, especially recently, more and more concerns about that. There were a couple of let's say interesting YouTube videos out there of people complaining about kill switches and things that allow to stop the vehicle from the outside and so on. But the fact is that actually things like driver monitoring system, they are all closed loop systems. So first of all, they are transforming the data, only short parcels of data, 5 to 10 seconds, that are needed to evaluate the driver state, transform that into a form of data that cannot be decrypted, and it cannot be retransformed into something that would be of any use for somebody. It's just information about the driver state. It doesn't tell you who it is, for example, and it doesn't leave the vehicle. So it's really a closed loop system. It's just used for a short period of time to evaluate the driver state and to interact then with the other systems in the vehicle. But there's no uploading to the cloud of what the driver is doing. If the driver is picking their nose or something like that, nobody will ever know it.
Well, as we all know, this is an IoT audience here. Let's frame the SDV for them directly. What makes the modern vehicle one of the most demanding edge and IoT platforms out there?
Yeah, I think we have everything that makes IoT in the vehicle nowadays. And I mean, the introduction that was given was pretty interesting. That it's probably the vehicle is probably the most frightening embodiment of IoT. So we have sensors, we have components, we have perception, right? We have compute, central compute. We have communication. We have communication networks. We have software on top of all of this. And probably the big difference to, I would say, a standard IoT, and again, I'm not an IoT specialist or expert, but the big difference that jumps to the eye probably is that it's all in the frame of potential life-threatening environment situations, because safety situations like a vehicle crash is not something that probably you find in your usual day-to-day IoT. But in the vehicle, you have this. You have all the components of it working together, including the communication part of it. And but in an environment that, on the one hand, needs to withstand conditions like vibration, temperatures, and so on that are automotive specific. I mean, I'm living in Michigan, so the temperatures that we have in the winter there, I don't wish them to most of you here. In the summer, it's becoming very hot as well, hotter than here actually. So it's an interesting temperature landscape. There's a lot of vibration. Michigan roads are not very good also sometimes. We have a lot of famous potholes. And so yeah, all of this needs to be, and it's not, I'm not only talking about Michigan. I mean, if you go all over the world, I mean, there are similar conditions. So we have all of this, and yeah, we and it has to be all the actions that go on in the vehicle. The decision making is in a very short time frame in a very harsh environment, and it needs to be boiled down to very to, let's say, split second decision making. In a very complex sensor and right. Compute environment.
All right, as we're drawn to a close, this is the last question for you, and this is the fun question. If you look 5 to 10 years out, what excites you the most, and what do you see is still the hardest problem to crack?
Mm-hmm. Okay, I think the automotive industry is somehow, it's a long road, it's a long river that flows along for more than hundreds of years now. So it has been a steady evolution. It has been speeding up significantly in the past couple of years, and it's exciting to imagine where it can go. It seems to be almost an exponential acceleration at the moment in terms of developments. I mean, some things are going fast, some a little bit less. I was imagining that my kids, they would never get a driver's license and then drive all autonomous vehicle. I don't think that's going to happen in the next 5 to 10 years, that all vehicles are going to be autonomous, but we are certainly going to see much more autonomous vehicles, much higher levels of autonomy in the vehicles. And what excites me about that is that I really believe that vehicles are getting safer with all of this. We have, it was mentioned before, we have, I think, more than 40,000 fatalities on North American streets every year for different reasons. And the automation of the vehicles and other technologies that we bring can certainly help to make driving much safer and save a lot of lives. So that is an exciting perspective as well. And the hard thing, yeah, I mean, it is a very complex industry. I mentioned before already partnerships and so on. I think a lot of things and a lot of industries and partners have come together to make this happen. But I think events like this here are a great opportunity to get all the stakeholders around the table and talk about this fun adventure for our future.
Well, Dirk, I learned so much today, so thank you. I appreciate it. And please give it up for our fireside chat.
Thank you.
Thank you, sir. Great job.